Okay, so now let's solve this other exercise, the 15-5. So let's read the problem together. Now, an ideal gas, okay, is slowly compressed at a constant pressure of 2 atm from 10 liters to 2 liters. What are they talking about? They are talking about this part of this plot. We are going from B, where the volume is 10 liters, and so all the way to 2, where the volume becomes 2 liters. And so let me try to make this a little bigger. So you see the unit here is liter. Okay, and they are saying that this pressure is, this PB that you see here, is 2 atm. Very well. In this process, some heat flows out of the gas. And so as this heat is flowing out of the gas, the, 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 the volume is contracting. Okay, we don't know how much heat is flowing out of the gas. Anyway, heat is flowing out, the gas is compressing, and the temperature drops. Then, from this point D to A, heat is then added to the gas. It's added from D to A, so the temperature is going to increase now, while the volume is not changing. So there is no work being done from D to A. It's isovolumetric. Okay, so from B to D, we are isobaric, constant pressure, but the volume is changing. There is work here. And from D to A, there is no work. The volume is not changing, just the pressure. Okay, what are the questions? Calculate A, the total work done by the gas in this whole process from B to D to A. So what is the total work? Well, we are going to compute the work from B to D and then the work from D to A. This will give us the total work for this whole process BDA. Okay, so let's come here. So the total work for this whole process BDA, I'll call this, let's write it like this, the work from B to D to A is going to be equal to the work from B to D plus the work from D to A. So this is the total work. Well, but we already said that from D to A there is no work because the volume is constant. So all that we need to compute is the work from B to D. Also, that's not too bad because that is work done at constant pressure. And so what we have to put is the pressure, which is that value PB, and the changing volume. So the final volume is the volume D minus the initial volume, the volume B. Okay, and how do we do that? Well, the pressure is 2 atm. Now you just have to be careful with the units. Okay, so it's 2 atm, but 2 atm, remember how we change units because we are going to give the answer in joules. So we are going to change the unit to international system. So these two we have to multiply by 1.01 10 to 5. And then comes the story about the volume. We are going from 10 liters to 2. So it's going to be minus 8 liters. But now we have to be careful because since we want to give the information in joule, we are not going to use liter. We want to change that and use cubic meters. If you go back to chapter 13, we talked about this conversion. Now 1 liter is 10 to minus 3 cubic meters. Okay, so we have to multiply this by 10 to minus 3 cubic meters. So now the answer is going to come out in joules, and it's going to be a negative value because we are compressing. Now the system itself is compressing, and so we get here 1 minus 6 10 to 3 joules. All right, very well. So part A is done. Then comes part, so this is part A. Then comes part B, which is the total heat flow. The total heat flow into, out of the gas, the whole thing. Because we know that from B to D, some heat is coming out, and then from D to A, we injected heat. So what is this total heat? Let's put it here, from B to D to A. So that's the question. Okay, now we could think about breaking into pieces, but there is something that is going to help us a lot in this process, in this problem. We go from B to D to A. But if you look point B and point A, they are part of an isothermal. You see the word here, isothermal, which means the temperature in point B and the temperature in point A is the same. All right? So we left this point B. Things happen along the way, and we went to point A. No? So many things happen along the way, but we left a certain temperature and we went back to the same temperature. So we know that for this whole process from B to D to A, the beginning and the end, the final state and the initial state have the same temperature, which means then there is no delta T in this whole process, the final minus the initial, so there is no delta U. The delta U is 0 for this whole process from B to D to A. So life becomes easier now because we can think about this equation. We can think about this equation for this whole process from B to D to A, B to D to A, and the work B to D to A. You may ask, why is she putting the minus sign here? Because this work is done by the system. The system is compressing by itself. Okay. Now, if delta U is 0, what is going to be Q? Q is just the work. So it's not so hard. And we already know what the work is minus 1.6 10 to 3 joules. Okay, so the system compressed by itself, so the work is negative. And because the temperature does not change, delta U is 0, so this heat is equal to this whole work. So at the end, the problem was not so hard.